Okay, Algebra 2, here we go into section 2.3 here, which is on linear functions and then slope-intercept form. So as we break this thing down here a little bit, the word linear, I'm hoping you guys are used to by now. It just means line, and functions we defined there in section 2.1. So functions that when we graph them that create straight lines with all their solutions are going to be linear functions. This is most of what you dealt with in Algebra 1. And there are multiple forms of linear functions that they can be written in, but today we're going to focus in on slope-intercept form while just having a little bit of a quick discussion about one other one that's out there as well. So here we go, guys. In part one of our notes, our definition of slope-intercept form is really given to us by this formula right over here. Y is equal to mx plus b is the general equation for slope-intercept form. And every time this year that I give you guys a formula with a whole bunch of variables in there, I should always give you guys an explanation of what all of those variables mean. So I'm really hoping you guys remember this from 2 years ago in Algebra 1, and you saw it last year in geometry as well. But here we go. The m in y equals mx plus b is your slope. Nobody really has a good reason for why we use the variable m for slope, but there you go. B is your y-intercept, the spot where the line crosses the y-axis. And there is a reason we use b for that, and I'll get to that a little bit later on. And then, this is the thing that a lot of people lose sight of here. That takes care of the m and the b, but the two variables there, the x and the y, which don't normally get values put in for them. This is true for linear functions, but also for every other type of function we're going to talk about this year. When you put together a value for x and a value for y into an ordered pair, that can represent any point that's located on that particular graph that would be a solution to your equation. Now, again, with some things that I'm hoping you guys remember about slope here, there's really 4 different types of lines that exist out there. So let's just draw real quick, and if you know this stuff just fine, there's really no need for you to put it in your notes here, but 4 types of line. One of them is rising from left to right, and a line that is rising is going to have a slope that's positive, greater than 0. A second type of line then, as you could probably guess, is one that is falling as we read it from left to right. So that's a line that's falling. If a rising line has a slope that's positive, you could probably guess that a falling line has a slope that is negative or less than 0. A third type of line is the one that isn't rising or falling from left to right. That is what we would call a horizontal line, and that has a slope that's not positive and not negative, so therefore the slope of that line would have to equal 0 right on the nose. And the fourth type of line is a funny one right here. That would be a vertical line that runs straight up and down from left to right. And a vertical line has a slope there that is undefined. That is not the same thing as saying that it's equal to 0, but what would happen on a case like this is if you were to measure the slope of that line, your rise over run, and I'm hoping you guys remember that's the definition of slope from back in the day, would end up giving you a rise of a number like 6. I'm just going to make something up in general, but the run would be 0. And anytime you go to divide a number by 0, that's when you end up with a quantity that's undefined. Unlike a horizontal line here, from here to here, where you would have a rise from one point to the next of 0 and a run of some other number like, I don't know, 8. 0 divided by any other number is equal to 0, and that's why we say that a horizontal line has a slope, it's just 0, but a vertical line doesn't have a slope at all. That's why it's undefined. Okay, so let's take a look at what we're going to do with this. Graphing linear functions is one of the big things that we do here. And in Algebra 1, you guys probably learned one way initially and then a second way later on to graph a linear function. The first way you learned, which is something you guys can always come back to, and we'll do this many, many times this year when we see something new and we're not sure how to graph it, is to remember that a graph is just a series of ordered pairs that are solutions to any equation. So what we could do here for this linear function, y is equal to x plus 3, is we could choose some random x values and plug them in. So I'm going to go ahead and pick some numbers like, oh, I don't know, I'm going to pick -5, I'm going to pick -3, I'm going to pick 0, and I'm going to pick 2. The domain of this function is really all real numbers, so you could pick anything in the world that you wanted for x. But now, to figure out what y is, we're going to put these values here in for x in this linear equation and see what we get for a y value. So when x is -5, we'll take -5 and add 3 to that. -5 plus 3 is -2. And we just found our first solution to this linear equation, the ordered pair -5, -2. Now, we never do this, but you're really making an ordered pair out of that. Your x value is -5, and your y value is -2. So we'll plot that. Starting from the origin, we'll go 5 units to the left. You wouldn't really make a dot there, guys, but just follow along with me. And then 2 units down, and that's where that point is going to be located. So I'll erase that first one there. And that's our first solution that we found to this linear function. But there's more. Let's plug in a -3 now. -3 plus 3 is going to get us 0. So our second solution is -3, 0. Starting at the origin, we go 3 units to the left, no units up or down. There's our second solution. The third x value we chose to put in was 0. So doing that right here, 0 plus 3 is going to get us 3. We have another solution now of 0, 3. So we don't move left or right at all. We just go up 3 units, and there you go. And at this point, everybody, since we all passed geometry, I might ask you guys to look at those 3 solutions that we've plotted so far and ask you if you notice anything. What I'm hoping you remember from last year is the idea that those are 3 collinear points. 3 points or more that all fall on the same line. So it really shouldn't surprise us then when we go to plug in this fourth x value I gave you of 2, we should get a fourth point that's also collinear with the first 3. Plugging in a 2 for x, 2 plus 3 is going to get us 5, and our fourth solution is 2, 5. Right 2, up 5, and that's going to get us to a point right here. Now, the important question here is this. How many solutions are there to a linear equation? We've just come up with 4 of them, but as I think you could tell, there are more. We could sit here all day long and keep coming up with x values and figuring out the y values that go along with them, and every single solution that we come up with, we could plot then and go ahead and come up with another point that's collinear with the rest. And if we were to draw a line between all of those points, we would end up with what looks like a linear graph, everybody, that looks something like that. And we would put arrows on both ends, which you should remember from geometry, because a line goes on forever. There's an infinite number of solutions. Okay. All of that was fun, everybody, but honestly, that's kind of the Algebra 1 or the pre-algebra way to come up with these solutions right here, and we're going to talk about something that's going to be much, much faster. So you know what? As fun as it all was, I'm going to erase that whole thing. I wouldn't expect you guys to do this in your notes, but follow along with me. We have an equation here that's solved for y. Y is all by itself, and that means that we are in slope-intercept form, which we wrote down on the previous slide. And from slope-intercept form, you guys should be able to tell me 2 things right away. What's your slope and what's your y-intercept? M, you'll remember, is the coefficient of this x right here. And when there is no coefficient listed, we remember that that means a coefficient of 1. And it's helpful when you're thinking about a slope to express it as a fraction. So that slope we would think of as 1 over 1. And remember, guys, that is your rise over your run for this particular line. B is the y-intercept, the number that's not being multiplied by x, but is added or subtracted, usually at the end of the expression, but it can also be at the beginning. And our y-intercept here is 3. Now, we can graph a line much more quickly than we did with all this work here if we just focus on these two pieces of information, and we start with this one right here. The y-intercept of 3 means that this line crosses the y-axis. Remember, guys, here's your y-axis. This vertical line right here in the middle crosses the y-axis at positive 3. So I'm going to go up 3 units and make a big fat dot right there. That's the first point on our line. And then we take a look at the slope. From that starting point we came up with right here, we are going to rise 1 unit and then run 1 unit to the right. All right, so what that means is from that first dot, I'm going to go up 1, right 1, and make a dot right there. And then I'll do the same thing again, up 1, right 1, up 1, right 1. And I'm kind of out of room now. We could reverse this now. We could go down 1, left 1, down 1, left 1, down 1, left 1, and do that as many times as we want. But I think you can see a series of collinear points again. So now we'll go ahead and draw the line between them all and draw the arrows at the end. And we have the same line here in red that we had in purple a few minutes ago. The table that we did first always works, but this idea of using slope and y-intercept is going to be much faster for us if we know for a fact that we're dealing with a linear function that is in slope-intercept form. Okay, so let's use that little shortcut idea to go a little faster through the rest of these. Here we go, graphing a linear function here. We are in slope-intercept form because we are solved for y. So take just a second. What's your slope and what's your y-intercept? Write those down for yourself here, guys. Okay, hopefully you got them. Our slope, the coefficient of x, is -2, and our y-intercept, the number being added at the end, is +4. We worry about the y-intercept first. And so, make this graph just a little bit bigger and easier to see here. Okay, our y-intercept is 4, so from the origin, our first move is always up or down. This one's going to be 4 units up. We're going to get a y-intercept, a point right there. And our slope is -2. To make a fraction out of that, we just put a 1 on the bottom. And that means that from this starting point, we have a rise of -2 and a run of +1. Rising -2 means we're going to go down 2. Running +1 means we're going to go right 1. So down 2, right 1 is going to get us our second ordered pair. And then I'll keep doing the same thing. Down 2, right 1, down 2, right 1, down 2, right 1. And if I wanted, I could reverse everything. I could go up 2 and left 1 and get a dot right there. And that's a series of collinear points, so we'll go ahead and connect them all with a straight line, which, by the way, is redundant, guys. You don't need to say straight line because there's no such thing in math as a curved line. And there we go. And just to prove to you guys what it is that we're accomplishing right here, let's take a look at one of these random points that we came up with. How about this one right over here? The coordinates of that red dot, it appears to be 3 units to the right of the origin and then 2 units down. So 3, -2 is a point that we came up with that's on the line. What that means, if we go back to what we said right over here on slide number 1, any xy point that we come up with is a point that's located on the line and or a solution to the equation. So watch what happens, guys, when we take this ordered pair and plug it in here for x and y. Our y value is right here, -2. That equals, here's our slope, -2. That gets multiplied by x. And our x value at that point is 3. And then we have a y-intercept of +4 at the end. And let's see what happens when we simplify that right side. -2 equals, well, -2 times 3 is -6 + 4. And -6 + 4 on the right side is equal to -2. This should surprise no one. We ended up with a true statement at the end. -2 is equal to -2. If I were to just pick some random point over here on the side, what did I pick there? I think that's -5 and 3. If I were to plug those values in here for x and y, we would not get a true statement. We would get something totally random here like, I don't know, what'd you get? 3 is equal to 14, I think is what would happen. That clearly is not true, and that's because this point is not a solution to this equation because it's not located on the line. Okay, so let's get rid of all that junk right there. That's what the solution to this graph here looks like. Okay, let's do one more in slope-intercept form. And I tell you what, actually, just for fun, I'm going to change that around just a little bit. Maybe you'll see why in a second. Let's make that y is equal to, and I'm going to go with a 5 minus 3/4 x. Now, you might notice that's almost the same thing that I had just a second ago, but I wanted to give you one, it just occurred to me now, where the order is a little bit messed up. So if this were to happen, first question, is it in slope-intercept form? Even though the x comes at the end, the answer is still yes. You're still solved for y. So we still should be able to figure out the slope and the y-intercept. Now, the slope, you guys, is not always the first number in the equation. The right way to think about it is that the slope is the coefficient of x. If you forgot the word coefficient, the number that a variable is being multiplied by. So here's your variable, x, and it's being multiplied by negative 3/4. Now, you can either put that negative out in front or on the top or on the bottom of a fraction. I think it's always better on the top, and I'll show you why in a second. The y-intercept is the number that normally is added at the end here, but that's not really the definition of it. It's the constant, the number being added or subtracted to or from the variable term. And in this case, that constant there is going to be 5. So it is possible that the y-intercept comes first and the slope comes second. It's just a question of how they present that equation to you. So with these two pieces of info, we should be good to graph this thing. We start with a y-intercept of 5. So from the origin, we go up 5 units and put a big dot right there. And now let's talk about our slope here. A rise of -3 and a run of 4 means that we're going to go down 3 units, 1, 2, 3, and then right 1, 2, 3, 4. Really try to stop yourself from saying what a lot of people say, which is the word over. A lot of people look at this slope here and tell me that it's down 3 over 4. My problem with that is everybody knows what up means. Everybody knows what down means. But the word over is kind of ambiguous because it can mean both left and right. So try not to let yourself say the word over. Try to go with left or right there. But the other thing I want to remind you guys is that you could have written this fraction as +3 over -4. That would have been a rise of 3, meaning 3 units up, and then a run of -4, which would have taken us to the left. So if I went back to this starting point right here and now thought about this slope, a rise of 3 would have me go up 1, 2, 3, and then left 1, 2, 3, 4. That's where we would have ended up right here. But you'll notice those 3 points that we came up with are all still collinear, so we can go ahead and draw the line, the one and only line that contains all 3 of those points. So you could have done this slope down 3, right 4, or up 3, left 4. Both of them are going to work just fine. Okay, the next thing we're going to talk about is a little bit of a cheat right here. Standard form is something that pops up just a little bit, and I think that standard form used to be a bigger deal in math than it is right now, mostly because it's easy to type into a textbook. Standard form is this equation right over here. AX plus BY is equal to C, and it's got 3 rules to it. Number 1, the coefficients of A and B and C all have to be integers. And in case you forgot from Algebra 1 what integer means, no fractions, no decimals. That's why back in the 1950s, standard form was easy to type in a textbook because you didn't have to worry about fractions. The second rule, A has to be positive. If that leading coefficient there is negative, you would just flip everything around from the left side to the right side and change the sign of everything. And the third one's a little bit tricky. A, B, and C all have to be, this is a phrase I learned in college, guys, relatively prime, which means that they have no common factor other than 1. Okay, so let me give you 3 examples. I would not write these down, you guys. 3 examples of something not in standard form, okay? Here's one of them. What if I gave you -3x plus 7y is equal to 11? That is not in standard form because it violates rule 2. A has to be positive, but this one has an A value that's negative. Okay, let's try another example here. What if I gave you something like 6x minus 1/2 y is equal to 5? That one is not in standard form because it violates rule 1. A, B, and C all have to be integers, no fractions. And right here we have a B value of negative 1/2. And the third one is a little bit weird. You could not have a standard form equation that looks like, for example, why don't I go with something like 15x plus 10y is equal to 35. Now in that equation right there, A, B, and C are all integers, 15, 10, 35. A is positive, so we're good there, but this one violates rule 3. There is a common factor that can be divided out from all three of those, and that's what you would need to do here in order to get that in standard form. As I think you can see, the common factor of all three of those is 5. So if you divide out a 5, you'd end up with a 3x plus 2y is equal to 7. And now that equation is in slope-intercept form. So standard form used to be really important. It really isn't anymore, you guys. And I'm going to give you one example where we're going to graph something that's in standard form, but I'm not going to teach you these old school rules that they exist, but they're really not that helpful. The way we're going to graph something in standard form is we're just going to cheat and we're going to put it into slope-intercept. So 3x plus 4y is equal to negative 12. And now the rules here, everybody, for slope-intercept form, let's just write this down. We are going to solve for y. And when we do that, we will be in slope-intercept form and we'll know what to do. So the first thing to do here to solve for y, we're going to subtract a 3x from each side of the equation. Those two terms are going to cancel, leaving us with 4y is equal to, and we've got a negative 12 minus 3x. Not like terms, they can't be combined. Most of us would prefer the x term to come first. So negative 3x minus 12, and there we go. And the last thing we need to do to solve for y, divide out that 4 by each term in the equation. Here, here, and here. Those cancel, and we end up with y equals. Now right here, guys, negative 3 doesn't divide evenly by 4, so we just write it as a fraction. Negative 3/4, and then I'll put the x at the end of that. And at the very end now, negative 12 divided by 4 is a minus 3, so there's our equation in slope-intercept form. Our slope is the coefficient of x, that's negative 3/4, and our y-intercept, careful now, is the number added at the end. Since they're subtracting a 3, that means that your y-intercept is actually negative 3. So let's graph that, everybody. A y-intercept of negative 3 brings us 3 units down from the origin right there, and a slope of negative 3/4 means we're going to go down 3 and right 4. Not over, but right. I don't really have room to do that again because it would get me down here somewhere and I'm off the graph just a little bit. So let's reverse that. Instead of going down 3, right 4, we could also go from the same y-intercept here. We could go up 3 and left 4 and get another point here. And I guess we have room to do it again. Up 3 and right 4 would get us right over here. And now it looks like I've got 4 collinear points. So I'll go ahead and draw the line between them. And there you go. So that's the way we're going to graph out of standard form, everybody. We're totally cheating. We're just converting it into slope-intercept form. I guess I could have written that right here, SIF. And then from slope-intercept form, most people know what to do. Okay, so that was our quick talk about slope-intercept form, a little bit about standard form, two funky little things that pop up from time to time here that kind of defy classification are horizontal and vertical lines. And so let's knock this one out real quick. A horizontal line right here, guys, is just an equation of the form y equals b, where b is the... This is where I'd ask you guys to think about that, and I'd also ask you to think, why would you guess that I chose the letter B, which we've been using all day? Well, as I hope you guessed, B is still the y-intercept of your line. Now, the reason this works, everybody, is because if you were to think about a horizontal line in slope-intercept form, y is equal to mx plus b. But if we go all the way back to the very first slide that we talked about, right over here, everybody, in this third graph, we talked about how in every horizontal line, your slope is automatically equal to 0. So if I went to y equals mx plus b and I knew this line was horizontal, the slope would have to be 0. Y is equal to 0 times your x coordinate plus b. Well, regardless of what your x value is, when you multiply it by 0, that just becomes 0. You get y equals 0 plus b, and there's no point in adding 0. You just end up with y equals b. And that's where that equation comes from, because the slope of every horizontal line is 0. So now, you guys, if I asked you to graph the horizontal, well, let me just say graph the line y equals -2, what I would hope you would recognize is this equation looks different than the ones that we saw before because there is no x. So anytime you have just y equals a constant, you should automatically be able to tell me that that's a horizontal line, and that this number right here, which is b, is your y-intercept. So our y-intercept here is -2. From the origin, we're going to go down 2 units and make a dot. That's where we start. And now, since there is no x here, we know that the line is horizontal, so we draw the one and only horizontal line that has a y-intercept of -2, and it looks like that. And we're done. Graphing horizontal lines is really, really easy if you recognize it as a horizontal line. Now, I do just want to make one point here, everybody. Going back to geometry, we just drew a line which contains how many points? Infinitely many. And if I were to just name a few of them, let me just go to this point right over here and ask you guys to think about the coordinates of that point. It looks like it's 4 units to the left of the origin and 2 units down from the origin, so that's -4, -2. How about our y-intercept right here? We did that already. That's the point 0, -2. And if I just chose one other random point over here on the right somewhere, I think that point is 7 to the right of the origin and 2 units down, -2. And I would ask you now, what do all 3 of these points have in common when it comes to their coordinates? And I'm hoping you recognize a y-coordinate of -2. Every single point on the line y equals -2 has a y-coordinate of -2. That's what they all have in common. That's the real reason why this is what the graph of y equals -2 looks like. They're really asking us to draw every single point that exists with a y-coordinate of -2, and there you go. So with that idea in mind, we're going to talk about the last thing right here, vertical lines. And if horizontal lines are given by the form y is equal to b, the equation for vertical lines are similar but different in an important way. Instead of y equals, this is now x equals. And instead of b, this is now equal to a. And if we go back a slide, everybody, we said, all right, in a horizontal line, b was the y-intercept. So if we had to guess over here, a is going to be the x-intercept, which is not really something that we ever talk about when we're graphing lines in slope-intercept form, but it becomes important, guys, when we're talking about vertical lines, because in most cases, a vertical line doesn't have a y-intercept. And I would love to show you guys how you go from y equals mx plus b and get a vertical line out of that, but this doesn't work the way the last one does, because before, when we were doing this work up here, we said that every horizontal line has a slope of 0, and then that term just wiped out. But here, vertical lines, going back to slide number 1, vertical lines have undefined slopes. And undefined means there is no number that you can put in here for m because it doesn't exist. Undefined is not the same thing as 0, so that reasoning really doesn't work right here. We just have to kind of plot this thing in the reverse way we did the last problem. If y equals b was a horizontal line, then x equals a is going to be a vertical line. And this number here, a, is your x-intercept. So on this problem now, I'm asking you guys to graph x equals 4. So what you should notice is that the equation has only an x but no y. And that tells you right away that this line is vertical. And the number you're given here, 4, is going to be your x-intercept. Now with a y-intercept, guys, we started thinking about the origin and then went either up or down from there to find where your line crossed the y-axis. But when we're talking about an x-intercept, think about the origin. Now we're moving either right or left to find out where this line crosses the x-axis. And here, everybody, our x-intercept on this line is going to be x equals positive 4. So 1, 2, 3, 4 units to the right. There's our x-intercept of 4, and we know that this line is vertical. That is all you need to know, and we'll draw this vertical line right there. And that's it. We're done. Just to kind of illustrate what we did, though, what's this point right here? I don't know. Looks like it's 4 units to the right and I think 5 units up. What's this point right here? 4 to the right, 1 unit up. What's this point right here? 4 to the right, 6 units down. Take a look. What do these 3 points all have in common? They all have an x-coordinate of 4. Hence the equation x equals 4. All right, so that's our explanation right there, guys, of horizontal and vertical lines. All right, everybody, that's a wrap on everything we have to cover here in section 2.3. So let's get working on that homework, and we'll come in and take some questions next time we're all together.